Hey there, so one of the types of problems that we often are calculating when we're using pH and equilibrium is to calculate the pH of a solution that includes either a weak base or a weak acid. So in class we've done calculations using calculations for a weak base and setting up an ICE table and then going through that whole process. And this time I'm going to set up this problem with a weak base instead of a weak acid starting out. The process is largely the same. The main difference is that if we're calculating the pH, we aren't actually going to end up with H+ in our equilibrium. So OBr- is a base, and we recognize that it is because it is an anion, and that's one of our keys for identifying Bronsted-Lowry bases, is that they're all going to have a negative charge. So if I think about this base, OBr-, we're still going to write the equilibrium with water, but it's going to be a base hydrolysis. So water is going to act as the acid. It's going to donate its H+ to the OBr-, and then what we're going to have left over there is OH-. So our ICE table is going to look a lot the same. We already have our initial concentration here, and we are always assuming that if we just have this solution, we don't have any of our product yet, and that's what we're looking at, is we're letting this change. So it's going to go forward and use up some of this OBr- and then keep on going. Okay, so our equilibrium concentrations are going to look a lot like this. Okay, the other thing that we need to recognize is that this is a Kb expression, and so we don't usually have Kb values in tables, and as a result what we're going to need to do is we're going to need to look up the Ka value for this HOBr. So I already did that for us. The Ka is equal to 2.3 times 10 to the minus 9, sorry. So we remember that Ka times Kb for a conjugate acid-base pair is equal to Kw. So we're going to calculate this Kb by solving for it. So we'll put in that value for Kw 1.01 times 10 to the minus 14, which you might need to look up if you're doing homework, and then put in the Ka value in the denominator there. So the Kb value that we get, let's see, 1.01 times 10 to the minus 14 divided by, don't forget your parentheses, or hopefully you're using your exponential functions, unlike on my calculator, which doesn't have them here because it's a cell phone. Okay, so 4.39 times 10 to the minus 6. Alright, so we've got our Kb value and we're ready to go. So the next step after we set up our ICE table is we're going to put in our values into our equilibrium constant expression. So Kb, if we want to put the B in there, is equal to the concentration of HOBr times OH- over OBr-. So that's going to be x times x over 0.0849 minus x is equal to 4.39 times 10 to the minus 6. So in class we talked about how if we've got a K value that's less than about 10 to the minus 6, we can approximate this this denominator and say, you know, the concentration is not going to be hugely affected by that. However, this is a somewhat dilute acid. It's not super concentrated, and our K value is sort of borderline. So I'm actually going to go all the way through and use the quadratic equation anyway, partially to model it and just to make sure. So the short version of that is that you can always use the quadratic equation and it will work. Sometimes we just make a little less work for ourselves by doing this approximation, but we will get a slightly more accurate number if we go ahead and go through the whole quadratic process. So let's go ahead and do that. Alright, so I'm going to bring this over to the other side by multiplying it. So 4.39 times 10 to the minus 6 times minus x. All right, so I'm going to multiply that through, distribute p times 0.0849, 3.73 times 10 to the minus 367. So that's the first term minus 4.39 times 10 to the minus 6x. Okay, so bringing everything over to the left-hand side is x squared plus 4.39 times 10 to the minus 6x. And of course, as always, if you need to pause the video and work through this because I'm going a little too fast, please do that. I just am trying to keep the videos as short as possible today, so of course please just pause things and move along at your own pace. Alright, so we've got a quadratic, so we recognize that our regular quadratic formula is of the formula, or form, I can talk today, really I can, ax squared plus bx plus c. So if we look at our coefficients here, the a value is going to be a 1, the b value is going to be this number right here, and the c value is going to be this number right here, including that negative sign. So x is equal to minus b, 4.39 times 10 to the minus 6. I can write that actually over here. So x is equal to minus b plus or minus, this is our generic, b squared minus 4ac all over 2a. So if we're using the quadratic equation, that's it in case you need the reminder. So negative b plus or minus the square root of b squared, 4.39 times 10 to the minus 6 squared minus 4 times 1 times minus 3.73 times 10 to the minus 7 all over 2 times 1. Okay, so my first step is usually to combine, to figure out what's underneath that quadratic sign there. This number here was left over, that's this guy right here. I'm going to have a negative times a negative, so that'll be positive, so that's going to be times 4. And then I have this number squared, so plus 4.39 times 10 to the minus 6 parentheses squared. Okay, so that's going to be my whole thing in there, and I probably would go and do that calculation again to double check. So please, if I get this number wrong, let me know. Sometimes I get math errors in here. Right. So now I'm going to take the square root of this one on my calculator. I'm just going to take it to the 0.5 power there. And I'm still going to rewrite this just to make sure that I don't have a problem with carrying numbers. So plus or minus, that would be 1.22 times 10 to the minus 3. Every time we are using the quadratic equation for a standard ICE table, we're pretty much always going to end up using the positive root here. So there are a few specialized situations that I don't think we'll see in our class where you would actually use the negative root, but I can't think of any offhand. So anyway, so we're going to have this number minus that number, minus 4.39. Oh, maybe I better put in some parentheses here. Nope, you're not doing that, Hart. Okay, we'll just go back. 4.39 times 10 to the minus 6. So that's not going to change our number very much, but it is changing it a little bit. Okay, make sure I didn't do a typo there. Oh, I did do a typo. Sorry about that. Let's fix it. 39 minus 6 divided by 2. Okay, so overall, x is going to be equal to 6.08 times 10 to the minus 4 molar. So in previous calculations, we've just automatically gone to saying, oh yeah, this is our concentration and we're good to go. But in this problem, because we had a weak base, we need to go back always and double check and say what was actually the thing we calculated, X. So now we need to look back up here at our ICE table and say, oh yeah, that's right. X was actually OH minus, not H3O plus minus. So now we're going to use the relationship. We remember that the pH plus the pOH is equal to 14 with the flexible number of significant digits there. And so that means that our pH is equal to 14 minus the pOH. So we can go ahead. This is also important that you not forget that there's an extra negative. So it's going to be minus a negative log of 6.08 times 10 to the minus 4 molar. Okay, so pH minus log of 6.08 times 10 to the minus 4. So the pOH is 3.216. And so 14 minus 3.216 is going to be our pH. So our pH is equal to 10.784 for this problem. And like always, we always want to go back and think about whether or not this makes sense. And if we think about this problem, we go back up and say, well, yeah, we had a weak base, right? This is OBR minus. It is a base. We expect to have a basic pH, and we do. So we should have a pH that is greater than 7, and that's what we get. I hope this was a helpful problem for you. And if you have any questions, please just let me know.